Hello everyone, welcome. This is part 11 of the Calculus Prep assignment. This is math from the void, the logical poetry that you need, delivered from nothingness. Okay, this part 11 is going to cover some exponential functions. We're going to continue with exponential and even logarithmic functions, how to work with them. Just a quick, brief reminder of an exponential function. It's going to look roughly like this. Y equals a times some base number b to the x power. This is sort of your standard exponential function, where increasing the power causes us to multiply by another factor of b. In fact, sometimes we'll put the term r. And you might remember that r is used to indicate a ratio. So r indicates a ratio or multiplier. Each increase of the exponent multiplies by the ratio. Right, so if I have x is a 2, that'll be r times r. If I have x is a 3, that's r times r times r. That sort of thing. So that's what an exponential model looks like. We're going to use this table of data in order to figure out a reasonable exponential model for the data. Remember that exponential models increase generally. And it makes sense that we're talking about the population of Nevada here. So the population of Nevada is increasing. This is in thousands, which means if we have 1,853 thousands, that actually means 1.85 million. Just an observation, in case you're curious about how many people are in Nevada. I certainly didn't know that. And it looks like as the years go on, 1 year at a time, the population is increasing, which makes sense. How much is it increasing by? It's really interesting to check these data tables and use them for what they're there for, to show you data. And so we can make quick comparisons here. If we just see that this goes up by 82. Okay, so the population increased by 82,000. And then it goes up by, not as much this time, it goes up by 63,000. And then it goes up by almost 100. It's going to be 97. And then this goes up by a little bit less. This is going to be 72. Lastly, we have that this goes up by 74. Now, in addition to it being useful to calculate these differences, how much it's increasing by, it's also useful to look at, especially with exponential models, it's really useful to look at the ratios. So the ratio of this number to what it was before tells you the multiplier of how much it grew. And for exponential models, we might not have the exact same multiplier, just like we didn't have the exact same change when we looked at the differences. So if we have the same exact ratio, that would be pretty freaky, but nature doesn't generally work in this completely, purely systematic way, although our predictions are generally fairly accurate. So if you want a really precise model for this growth, you would have to use maybe Desmos or some kind of statistics to get the best fit line, sort of like we got the line of best fit earlier, but we got a linear model. You can do the same process with some data and extract an exponential model that captures most of the data. So let's see what they want us to do here. Yeah, sure enough, part A says to compute the ratios. So that's what we have to focus on. Compute the ratios. What ratios? Of the population in 1 year by, so this is basically saying this thing is going to go on top. Remember, a ratio is just a fraction. Population in 1 year by the population the previous year. So that's what tells you is on the bottom of the fraction. Okay, so we're basically just computing this kind of a ratio. So we might call this the multiplier. And we'll call it, I guess we'll just label them R1, R2, all the way until we get to, let's see, 1, 2, 3, 4, 5, R5. With R5 being the ratio from here to here. I know there are 6 values, but there are only 5 ratios because the first one doesn't really have anything to compare it to before it. So you can definitely use the calculator for this. If you were to write it by hand, it's great if you know how to do that, but it's going to take a while. So let's do this together. 1.935 divided by 0.853. This is going to be a ratio of 1.044252. I guess 5 decimal places is probably enough. Okay, let's keep doing this idea. You'll notice that the change in the next one is less, so I'm guessing this ratio is going to be even less. 1998 divided by 1935. Yep, just as predicted, this is going to be 1.0325, and I'm going to put a 6 because it's really a 5/8, but I think we can round that to a 6. The next ratio, R3, 2095, 1998, and you can skip by this if you're already doing it on your calculator, or if you've already done it. I'm just showing you in real time how long it could reasonably take. I think that's fair. So this is going to be 0.048548. I'm just going to round that up to 0.4855. All right, 2 more ratios. Go ahead and divide those. 1.0343, and a 7 follows it, so I'm going to round that up to a 7. And then our last ratio, 2241, 2167, 1.034. So these are all within the same range. This ends up a 4/8, so I'm going to round it to a 5. These are all within roughly the same range here, but those are the ratios. Based on part A, create an exponential model. Now, because the ratios are not the same, we cannot use one of them and say it's going to work for all data values. That's simply not the case. Like I mentioned earlier, with statistical models or some kind of statistics calculator which Desmos has programmed into it, you could generate an exponential model that's best fitting for all of these, like as an average. But realistically speaking, we're just going to take something that seems to be in the average, and that should be acceptable. I'd like to choose one that's actually represented here, and these are kind of spread apart, to be honest. So I think it would be somewhere in like the 1.038 range is what I'm feeling. So let's go ahead and say that. Let's go ahead and say we're going to use R equals 1.038. And there are different methods. Like you could average the ratios and try to get your selected value that way. I just kind of ballparked it. I don't think the statistical models use a literal average. They might use some other more complicated calculation. Okay, well, we need to fit the data now. So we're going to say that, let's call it P, the population P, is equal to some value A, which we don't know, Oh, I see why it might have been a good idea to pick one of the values that's represented on here. Because if we do that, we're given an initial value. Yeah, so in fact, let's do that. Let's write an equation for each of these, and I'll just put them right next to the point, and I'll also explain the function. So we're going to have P of t is equal to some value. We'll pretend that we don't know that it's going to be 1,853, but that's what it's going to be. Some value times the ratio of, what was this one, 1.04425. And then we're going to send it to the power of t. In this case, t is the number of years since 1998. And also t has to be greater than or equal to 0. If it's 1998, then t is equal to 0. What happens if t is equal to 0? Well, I know the population when t is equal to 0. It's going to be 1,853. And that's going to equal some a value. Again, we're going to pretend we don't know what it is. But then this is going to become 1.04425 to the 0. And any non-zero to the 0, this just becomes 1. So this says a is simply equal to 1853. That's the starting value. And so we can make a model based on that starting value. And then if you wanted to use a different r value from that reference point as your starting point, I mean, then you're getting just a little more technical, which is going to give you a slightly more accurate model, but it's probably a bit more of a pain to write it out. So here we're just going to have P of t is 1,853, and we'll keep the ratio that we found from the year 1998 to the year 1999. And that's what's going to take us there. Okay, so we can box that answer. Like I said, if you wanted to, you could use, realistically, you could use any one of these as your starting value, and you could use t as a year since 1999. However, just keep in mind that if you make your starting point somewhere over here, you're going to have to allow values of t that are negative in order to go backwards and look at certain populations from earlier years. You would have to allow us to go sort of, not back in time, but kind of, yeah, back in time. Okay, so that's the model that they want in part B. So I guess we'll scrap this 1.038 business. We said it was what? We said it was 1.04425 times, oh, whoopsie. So we have P of t is 1,853, 1.04425. That is a perfectly acceptable equation here. We're probably going to have to use this model. Yep, exactly. Use your model to predict the population of Nevada in 2010. We can compare it to the actual value too, if we look up the value. I should also mention this, by the way. T greater than or equal to 0. And also t is years after 1998. Okay, so that's what's going to tell us to plug in 2010 minus 1998, or in other words, 12. And we can simply plug it into the model. P of 12 is going to be 1,835 times 1.04425 to the 12th power. Go ahead and plug that into a calculator. See what you get. I'm getting 3,085.24655. Now this is in thousands, so really what that means is it's like 3 million, almost 3.1 million. And I'm curious, what's the population in Nevada in 2010? I have to look up 2010. So 2010 Nevada population. It's crazy that we can just look this up on our phones, by the way. It was 2.702 million. And actually, if you notice the graph, if you take a look at the Nevada population graph, you can actually see that it is looking kind of exponential, but then starts going sort of flat, like linear. Actually, I'll draw it. It's something like, kind of starts to straighten out, whereas our model follows like, an exponential sort of increase kind of thing. But it looks like it kind of flattened out at some point. Why is that? I have no idea. I do not study humanities. I don't know. Okay. Here we are. Now we're going to solve equations. And I'm going to remind you about something. Equations of exponentials or equations of logarithmic functions, they're inverses of each other. So we're going to take advantage of the fact that inverses, what do inverses do? Inverses, they undo each other. An exponential is when you have a variable in the exponent. A logarithm does the inverse of that. It does the opposite of that. It takes an exponent and turns it into a regular number. So in order to solve these equations, we're going to have to turn a logarithmic into an exponential, not right away, but at some point. And to solve an exponential, we're going to have to turn it into a logarithmic, not right away, but at some point. So if you can understand that, it's going to be very helpful. Now we're also going to have to use some techniques with logarithms. These properties of logarithms that we have. They allow us to combine logarithms and simplify their expressions in a certain way, as long as we have the same base, which we do. Both are base 2. First, we're going to use the power property of logarithms, which says a number being in front of the log is the same thing as putting that number as the exponent of this argument, which is inside the log. So the 2 is a power now on the x plus 3. Next step is we need to condense these logs because they're being subtracted. We're allowed to condense them together using division of these arguments on the inside. So the positive one is x plus 3 squared. That's going to be the numerator, divided by x plus 1. And now we're going to change this to exponential form. We cannot do anything else with the logarithms. We've condensed it together. And then once we condense, we will change form. Then we will expand. So change form, this is the base. And the logarithm is equal to an exponent. So this is the 3 exponent. That's going to be equal to x plus 3 squared over x plus 1. Now we're ready to solve this as a normal quadratic situation. Let's multiply both sides by x plus 1. And we multiply that to the 2 cubed, which is just 8, right? So this shouldn't be a big surprise. 8x plus 8 equals to x plus 3 squared. And after you expand, you'll see clearly now that this is a quadratic. And you can solve it like a quadratic by moving everything over to one side. And hopefully you recognize this. Not surprised if you don't, but if you recognize this, it is a perfect square trinomial. Maybe you would figure that out by just factoring it normally. And now we can set this equal to 0. If you factor it normally, you'll get x minus 1, x minus 1. So that's just x minus 1 squared. And therefore the solution to this equation is x equals 1. But is it really the solution? We have to check. Earlier in this prep assignment, we had a discussion on domain restrictions. So hopefully, if you were really locked in, you were asking yourself, what about the domain of these logs? You should always be thinking about the domain of the logs. Well, let's just make sure that we know the domain of this log. this has to be greater than 0, which means x has to be greater than -3. Okay, checks out. We got x equals to 1. That's definitely greater than -3. No problems here. Then for this one, x plus 1 greater than 0. That means x is greater than -1. So that's the restriction. And again, it checks out. X is equal to 1, which is definitely greater than -1. Great. So this solution is verified. Let's move on to the exponential equation. In the exponential equation, we're going to have to, sorry if it's kind of blurry, I enlarged these images like on the website, and yeah, it's possible some things are getting lost. After all, everything is just 99.99% empty space. Atoms aren't really hugged up as closely as we think they are. Okay, anyways, let's solve this exponential equation. What we're going to do is a similar method or a similar broad idea to what we did in the logarithmic expression. Was we sort of simplified everything so that just the logarithmic expression was on one side. We're going to do the same thing with exponential. We're going to subtract 6 on both sides. Then we're going to divide 2 on both sides. Oops, I don't know where that came from. Equals to 4. We're going to divide 2 on both sides. And then we're going to have e to the 2x. Oh, I know where that came from. Because it's part of the exponent, dude. 2x minus 1 equals 4. Then we divide by 2. We get e to the 2x minus 1 equals 2. Now at this point, we need to use the inverse property, because I can't access this exponent. I can't access the variable in that exponent. But if I put things in terms of logarithm, that means I'm putting things in terms of exponent. And so I can talk about the exponent like it's a linear expression. I can speak about the exponent because this exponent is linear, 2x minus 1. So when I turn this equation into a logarithmic relationship, then I'm talking in terms strictly of the exponent. So let's take a log of both sides, as we say. We're going to do ln of both sides, which cancels the e, because ln of e is just 1. And on the right side, I will have ln of 2, log base e of 2. And now I can solve this in a strict linear terms, because it's just a linear equation now. We add 1, add 1. We have 2x equals ln of 2 plus 1. And x equals ln of 2 plus 1 all over 2. So this expresses a value of x in terms of an exponent. But it doesn't really look like it because you don't see a base in an exponent. But this logarithm means exponent. And I always encourage you in algebra to plug this in, check, see what you get. Make sure the left side is equal to the right side with your proposed solution. Okay, great. We're going to finish off strong with these two problems here, 28 and 29. In this case, now that you're a pro at solving logarithmic equations, we're going to solve the equation for y. We want to get the y by itself, which means it's okay if x's are flying around everywhere. That's okay. We'll be using properties of exponents and properties of logarithms, because after all, logarithms are just exponents. The technique we used in the previous problems is still going to carry on here. We want to get this logarithmic expression by itself, which is pretty easy to do actually if you just add the ln of 2, right? So what's the challenge? Why is this problem trickier? Because we can use some techniques in between to make our work a lot easier. For example, if we have ln of 2 plus ln of x, Now we can rewrite this equation. I guess I'll write it a little smaller. Now we can rewrite this equation as ln y minus 1 equals x plus, what do I do with these two if I'm adding logs with the same base? I multiply them. So this is simply ln of 2x. Okay. Now this might seem kind of tricky to work with, but it's not so tricky to work with. How do we work with an equation that is simplified to the logarithm on one side? We simply use the exponential form now. Why? Because I cannot access this, similar to how I could not access the exponent when I was in exponential form. Where was that? Yes, that was down here. I could not access the exponent, the 2x minus 1. I could not access that. I had to change it to logarithmic form, which talks in strictly exponent terms, and then I could access that. So in this case, I cannot access the inside. I would have to turn this to exponential form, and then it would just be on the ground, on the base floor. It will not be in the exponent. So let's raise everything to the e. So like e to this power equals e to, be very careful here, to this power. And the ln, of course, just cancels out. This is y minus 1. But what happens on the right side? Well, you have to keep in mind that we're working with exponents here. Adding exponents can be broken up as multiplication. So what do I mean by this? I'll show you a small diagram, even though you should know this pretty well. If I have x to the a power times x to the b power, this is x to the ab power. And this is because x to the a power means I have a multiples. I have a copies of x. X to the b power means I have b copies. Oh, whoops, I wrote this expression incorrectly. A plus b. X to the b means I have b copies. And therefore, if I combine these all together, I have a copies and b copies. Therefore, I have a plus b copies. Okay? So therefore, I can break up this expression as e to the x times e to the ln 2x. And that's the part which will simplify very nicely. We have y minus 1 equals e to the x times 2x. And therefore, we can solve the y by simply adding 1 to both sides. So 2x e to the x plus 1. There, we have it. So as you can see, there were some techniques that we had to use, such as multiplying the 2 and the x when we add the logs. But then we also had to use that same property, but in exponential form, where we had these two exponents being added together. Therefore, it means multiplication. E to the x times e to the ln 2x. Great. Now, the ultimate test of whether or not you can simplify a logarithm by using the properties of the logarithm. These will be properties that you're expected to know. I'm not going to write them here. You know that you've seen them before. If you're very curious and cannot remember, you need to look them up and you need to write them down somewhere. Hopefully you vaguely remember them, though. Well, hopefully you remember them very well. But here in the board, we want to remind you. You're just a rememberer. Okay, let's look at this. First, we want to express this with log base k. That's the base for all the logs here. And then we want to use the square root. It's not really a square root. If you cannot see that, it's a 5, so it's a fifth root. We want to express this as a 1/5 power. And then we'll put what's inside. We have x cubed, we have y squared, and then over y to the 1/2 power. Okay, so this is a good start so far. Let's simplify the inside. What do I mean? This is a fraction, but it doesn't really need to be a fraction. We could simplify that. So this is just using some basic algebra. I'm just simplifying exponents. So this would be y to the 3/2 power. Figure out y, work on why that's true. And this is to the 1/5. So we have not done any log properties yet. We just used some basic algebra. And we used the simplifying the root by putting a power with the fraction. Now we can use the log properties. The first one, hopefully you remember this from earlier. The power on the argument of the logarithm can just go in the front. So that is pretty nice. It already looks a little bit less claustrophobic inside of here. X cubed y to the 3/2. And let's use the multiplication property, which says we can, instead of writing this as multiplication, we can put log k of x cubed plus, we can add the logarithms, log k y to the 3/2. And the reason I put this in brackets is because the 1/5 needs to multiply this whole thing. Therefore, the 1/5 needs to multiply the expansion. And we'll have 1/5, we'll use the power property as well. One more time. So when we distribute the 1/5 to the first expression, we'll have 3/5 log k of x. And then when we distribute this to the 1/5, I guess we're sort of distributing it the other way, we'll have 3/10. Oops, different color. So I put the 1/5 on both of them, but I just multiplied their power in front. That's all I did. And the reason why this could be better is because some problems will give you a value for log kx. They might say something, you've probably seen some questions like this. They might say, given that log kx equals like 0.6, that is an ugly k. I don't like the k. Sorry, k. I could do better. 0.6, and log k of y is some other value, I don't know, 12 or something. And you would basically have to peel this logarithm apart very carefully, and then you would plug in the given values to make this go into some kind of decimal. Okay, I know we really picked up the pace there at the end. I wanted to use the momentum that we developed from the first two problems to really get you comfortable with looking at logarithmic equations. We're not completely done with logarithms, but we're getting close. So keep journeying on. I'll see you next time.